In today's video, I am going to explain a problem on non-homogeneous recurrence relation, and this topic is related to the discrete mathematics. And here is the problem on the screen. We have to solve the recurrence relation an is equal to 4an minus 1 minus 4an minus 2 plus 3n plus 2 power n. And given the initial conditions are a0 is equal to 1 and a1 is equal to again 1. So let's get started to solve this. The given recurrence relation is an minus 4an minus 1 plus 4an minus 2 is equal to, this is 3n plus 2 power n. See here, this is the RHS part. If there is an RHS term, we say that it is a non-homogeneous recurrence relation. And now I am going to write the recurrence. The homogeneous recurrence relation is, now the homogeneous recurrence relation is an minus 4an minus 1 plus 4an minus 2 is equal to 0. Now I am going to write its characteristic equation. So now its characteristic equation is see, this is of order 2, so that we can write as r square minus 4r plus 1. So here this is 4. This is r square minus 4r plus 4 is equal to 0. Now I have to find out the roots for it. For finding the roots, see what I'll do. So this can be written as r minus 2 whole square is equal to 0, and r values are, this is r minus 2, this is r minus 2 is equal to 0. Therefore r is equal to 2 comma 2. We got the equal roots. Therefore our homogeneous solution can be written as, therefore the homogeneous solution is, see here, the homogeneous solution is an of h is equal to, as these are equal roots, this can be written as c1 plus a c2n into, this is 2 power n. So this is 2 power n. And now coming to the particular solution. So here we have, from the RHS side, we have 3n plus 2 power n. So this is a linear polynomial and this is of a power n, that is 2 power n. So there are of 2 parts. So we have to split into 2 parts. See, first of all I am writing the RHS part is equal to the RHS. The RHS of the recurrence relation is, the RHS of the recurrence relation is, this is 3n plus 2 power n. This is 3n plus 2 power n. So we have 2 different parts. So different parts are, this is a linear polynomial and this is of the form 2 power n. So the particular solution will be, an at p is equal to, that is the particular solution 1 plus the particular solution 2. So particular solution 1 will be of the linear form 3n, and for particular solution 2 will be of the form for 2 power n. So this is 2 power n. First of all I am selecting the RHS part is 3n, since, see here, since the part of RHS is 3n, the first one I am selecting. Since the part is 3n, and let us assume the particular solution. See how the particular solution will be. The particular solution will be, let the particular solution, the P1 will be of the form, this is D0 plus D1n, as it is a linear polynomial. So we have to substitute the same thing in the given recurrence relation. See here, what is the recurrence relation? So the recurrence relation will be, from the question, what is it? The recurrence relation will be, this is an minus 4an minus 1 plus 4an minus 2 is equal to, so here RHS part we have to take as 3n. So this is the recurrence relation after taking 3n as RHS. Now we have to substitute this one. So this will be, what is an? An is equal to, this is d naught plus d1n. This is 4 times of, in place of n we have to write n minus 1. That is d naught plus n minus times of d1 plus again 4 times of, this is d naught plus n minus 2 times of again d1 is equal to 3n. Now I am going to solve this. See here, so this will be, if I take d naught common, so if I take d naught, so this will be d naught. See here, so this is d naught, and this is again d naught, and this is again d naught. So this is d naught, and this, if I multiply with 4, this will be minus 4 d naught, and this is again plus 4 d naught. And coming to d1, see here, if I take d1 common, see what are the d1 parts. So this is d1, this is d1, this is d1. So the quotient of d1 here is n, and here the quotient of d1 here is minus 4 times of n minus 1, and here the quotient is 4 times of this is n minus 2. N minus 2 is equal to, this is 3n. So here, if I cancel this 4d naught plus 4d naught and minus 4d naught, and what happens here? So this will be only d naught plus d1 times of, if I keep on multiplying, this is n minus 4n plus 4, and this is again 4n, and this is 8 is equal to, this is 3n. So now if I cancel this plus 4n and minus 4n and see what remains. So this will be d naught plus d1 times of, this is n, and this is plus 4 minus 8. So this will be minus 4 is equal to, this is 3n. So I got an equation as d naught d naught plus d1 times of n minus 4 into, this is 3n. So if I compare the quotient here, this will be d naught plus d1n minus 4 d1 is equal to 3n sum plus 0. So see here, what are the constants here? D naught minus 4 d1, and here this is d1 into n is equal to 3 naught plus 0. So if I compare the quotients of n on both sides and constants on both sides, on comparing the coefficients, of n and constants on both sides, see what happens here. So this is d1 is equal to 3, and the next one, if I compare the constants, this will be d naught minus 4 d1 is equal to 0. So if I substitute the d1 value here, d naught minus 4 into 3 is equal to 0. So d naught minus 12 is equal to 0, and see here, d naught value is equal to 12. So here d1 value is equal to 3. So I got the value of d1 as 3 and d naught as 12, and here the particular solution. Therefore the particular solution 1 will be the particular solution an of p1 is equal to, we concluded that d naught plus d1, and we assumed. Therefore this value will be an of the first particular solution is equal to, what is d naught? This is 12 plus, what is d1? This is 3. This is 3n. So we got the first value as 12 plus 3n, and now we have to consider the second particular solution. See here, so for 3n it is completed. For 2 power n we have to take. So RHS, since the second equation 3n is equal to, the second part is 2 power n. So the second part here is, since the part of RHS is 2 power n, and 2 is and 2 is the double root, see here, double root of the characteristic equation So let us assume the particular solution, that is an. The second particular solution is, see here, this is d n square into 2 power n. Now we have to substitute in the given recurrence relation. So what is the given recurrence relation here? The given recurrence relation is equal to, so the equation here is an. So from the question it is the given recurrence relation. I'll show you. See here, this is the recurrence relation, that is, so the second particular solution we assumed, let the second particular solution be, see here, so this is nothing but d n square into 2 power n. Now we have to substitute this in the equation, recurrence relation here, that is an minus 4an minus 1 plus 4an minus 2 is equal to, this time 2 power n. 2 power n we are selecting, and if I substitute here all the values, that it will be d n square into 2 power n minus 4 times of, in place of n we have to keep n minus 1. So this is n minus 1 whole square into 2 power n minus 1 and 4 times of n minus 2 d. So in place of n we have to keep n minus 2 whole square, and this is 2 power n minus 2 is equal to 2 power n. Clear? Now see here, this is d n square 2 power n 4 times of, so this can be written as d n minus 1 whole square, this is 2 power n by 2, and 4 times of d, this is n minus 2 whole square, this is 2 power n by 2 square, this is 4, is equal to 2 power n. So now if I cancel this one, so if I cancel this one for 2 times, if I cancel this one for 1 time, and if I take 2 power n common, see here, there is 2 power n here, 2 power n here, 2 power n here, and 2 power n here. From LHS and RHS, if I take common and cancel, then see what happens here. Then 2 power n if I take, then this will be d n square minus d times of n minus 1 whole square plus d times of, this is n minus 2 whole square is equal to, this is 2 power n. Now if I cancel this 2 power n on both sides, see what remains here. So in this equation, what remains, see here, this will be d n square minus, if I expand this one, this is a square plus b square minus 2ab into d, and this will be a square plus b square minus 2ab into d. So this time, so if I cancel, so 1 remains here. So we need the values of d here. So for getting the values, we have to substitute, we have to put n is equal to 0. If we put n is equal to 0, see what happens. So this will be 0. So this value will be 0. This will be 0 plus 1 minus 0 into d, and this is again 0 plus 4 minus 0 into d is equal to 1. See here, this will be minus d and this is 4d. See here, in this equation we cancelled for 2 times, so we have to write here 2. So here we have to write 2, and see this will be of 2, and this is minus 2d, and here what remains, plus 4d is equal to 1. So this will be 2d is equal to 1 and d value is equal to half. So we got the value of d as half. So now I am going to substitute in this equation the second particular integral. Therefore, the second particular solution is, therefore, the particular solution that is an, second particular solution is equal to dn square into 2 power n. Therefore, an of the second particular solution, d is equal to half, that is n square into 2 power n. That is, the second particular solution will be n square into 2 power n minus 1. So this is our second particular solution. So now we need the total particular solution. So this is B, and just now we calculated this one, the particular solution. Okay, not this. So this is the first particular solution, that is D0 plus D1n, and we got the value as 12 plus 3n. So this is equation number A. So now we have a particular solution, therefore the total particular solution is, therefore the particular solution is, an is equal to an of P is equal to an at the first particular solution, an at the second particular solution. So that will be, see here, an at P is equal to, what is the first particular solution? The first particular solution is nothing but 12 plus 3n. So this value is 12 plus 3n, and the second particular solution here is n square. So this is n square into 2 power n minus 1, and the homogeneous solution here will be, see, we have homogeneous solution as the homogeneous solution. The homogeneous solution is an at h is equal to, see, I'll show you. First we did homogeneous solution. So this is the homogeneous solution. The homogeneous solution is, see here, an at h is equal to C1 plus C2n into 2 power n. So this is C1 plus C2n into 2 power n, as we got two equal roots. Now the general solution is, therefore the general solution will be, the general solution an is equal to, this is the homogeneous solution plus the particular solution. So the general solution an is equal to the homogeneous solution plus the general solution. So if we add up all these, then an will be, what is the homogeneous solution here? Homogeneous solution is nothing but, this is C1 plus C2n into 2 power n, plus the particular solution here is this one, that is 12 plus 3n, plus this is n square into 2 power n minus 1. So this is the general solution. After getting the general solution, we have certain initial conditions. So here the initial conditions are, so from the question it is given that the initial conditions A0 is equal to 1 and A1 is again equal to 1. So we have initial conditions as A0 is equal to 1 and A1 is equal to 1. For that we have to put n is equal to 0. Put n is equal to 0. If we keep n is equal to 0, then see A0 value will be C0 plus 0. This is 2 power 0. This is 12. If we put n is equal to 0, this will be 0 and this will be 0. So the A0 value will be, this is a C1 plus 12. What is A0 from here? A0 is 1. So 1 is equal to C1 plus 12 and C1 is 1 minus 12 and C1 value is equal to minus 11. So we got the value of C1 as minus 11. And see, if we keep n is equal to 1, so keep n is equal to 1 here in this equation. So if we put n is equal to 1, see what happens in this. So this will be A1 is equal to C1. That is C1 plus C2 into 1. This is again 2 power 1 plus 12 plus 3 into 1. So this is 3 into 1 and again 1 here. So this is 1 square and 2 power 1 minus 1. So after substituting we got this. So this is a C1 plus a C2 into 2. This is 12 plus 3 plus this is anything to the power of 0 is 1. So this will be 1. So what is A1 value? So A1 is equal to 1. So if I substitute here, this will be 1 is equal to 2C1. If I multiply, this is 2C2 and this is 15 plus 1. This value is 16, or else we can cancel. So this is 16. So if I send to other side, this is 1 minus 16. This is 2C1. What is C1 value? C1 value is minus 11 plus 2C2. So this is minus 15, this is minus 22 plus 2c2, and here, so if I send to other side, this will be 22 minus 15 is equal to 2c2. This is 7 is equal to 2c2, and c2 value is equal to 7 by 2. So we got the value of C2 as this is 7 by 2. After getting C1 and C2, now we have to substitute in this general equation. So if I substitute in the general equation, see what happens. So our general equation is an is equal to, this is a C1 plus a C2n into 2 power n plus 12 plus 3n plus this is n square into 2 power n minus 1. We got C1 value as minus 11 and C2 value as 7 by 2. See here, we got C1 value as minus 11 and C2 value as 7 by 2. So if I substitute the same thing here, then what happens here? So an value will be, what is C1? Minus 11 plus this is 7 by 2n into this is 2 power n plus 12 plus 3n plus this is n square into 2 power n minus 1. This is 2 power n minus 1. So we can write this as an is equal to, if I take 2 LCM, so if I take 2 LCM and calculate, or else this will be 7 by 2n minus 11 2 power n plus 12 plus 3 power n plus this is n square into 2 power n minus 1. And this is how we have to solve, and this is so simple if you follow these simple steps here. First of all, the question is given like this. The question is given like this, and we have to write the homogeneous recurrent solution, and after finding the roots we have the homogeneous solution as C1 plus C2n into 2 power n. Since the RHS is 3n plus 2 power n, we have to split into two parts. The first one is the linear solution and the second one is of the form 2 power n. So we have to split into two particular solutions. So since the part of RHS is 3n, so we can write this as d0 plus d1n. So if I substitute the same thing, so if I substitute here, see, I'll show you. If I substitute d0 plus d1, so we got the first value as after substituting the value here, d0 plus d1n in this equation and solving. So we got d1 as 3 and d0 as 12, and the first particular solution will be d0 plus d1n. d0 value is 12 and d1 value is 3. So since the part of the RHS is 2 power n, so and 2 is the double root of the characteristic equation, so we have to assume the second particular solution as dn square into 2 power n. So if I substitute in this given recurrence relation, so for finding the value of d, we have to put n is equal to 0 in the given equation. We got d value as half, and in this place of d, if we substitute half, and this will be the second particular solution. And after getting the first particular solution and the second particular solution, so we have to add up these two. So the RHS part is, first one is 3n and the second one is 2 power n. So the first value, it is 12 plus 3n. This is 12 plus, so we got this value as 12 plus 3n, and the second value as n square into 2 power n minus 1. And also we know that the homogeneous solution is C1 plus C2 n into 2 power n. So the general solution will be adding up of homogeneous solution plus the particular solution. So this will be the general solution. So we have initial conditions as a0 is equal to 1 and a1 is equal to 1. So if we substitute, we got the values of C1 and C2 as C1 and C2 values as minus 11 and 7 by 2 and 7 by 2. So now we have to substitute all the values here. So C1 as minus 11 and C2 as minus, so this one C2 as a 7 by 2, and if we substitute, we'll be getting the solution. See here, C1 as minus 11 and C2 as 7 by 2, and this is the general solution. This is how we have to solve. So there are two parts for the particular solution, and carefully we have to solve, and if you really like, you know what to do, please practice.